Hello, everybody. So this week I am covering chapter 6 of the Gordis Epidemiology textbook. So let's go ahead and get started. And some pictures for you all. Good stuff here. Lots of good stuff. All right, so let's just start talking about death. That's a topic that's inevitable to all of us, unfortunately. We don't live forever unless you're a vampire. I know it's the season for vampires, but I ain't no vampire, and neither are you. So we have to deal with death. There's different ways that we measure death, right? One of them is using case fatality. That's the proportion of individuals diagnosed with a disease who end up dying of that disease. More useful for acute diseases than diseases that have take a longer time. The natural history, so natural history of the disease, when we look at a disease, that's from the infection to or whatever the inception of the disease, because it doesn't have to be a disease caused by a pathogen, right? Until it could be a chronic disease too, caused by lifestyle behaviors. But from the inception of the disease process to the termination point, which in this case we're focusing on death. Case fatalities, the proportion of deaths from cases out of the cases. So it's just the number of deaths divided by the number of cases. Some diseases have a higher case fatality, such as Ebola, which has a case fatality of about 90%. So that means a 90% chance one will die if one is infected with Ebola. And a lot of that has to do with where a person is infected too. If you live in a country that doesn't have the same kind of medical care as in a more a richer country, I think the case fatality will be higher. Diseases like COVID-19, which obviously caused a lot of distress for many people, had a much lower case fatality. So these are some data from back during the COVID period, when we were still all locked down, I believe. The case fatality for COVID was, and this was in Pennsylvania, was at that time point 1.45%. So it wasn't as fatal as Ebola, obviously 90% versus 1.45%, just caused a lot of problems. Again, if we were to restrict this to the population of older individuals or individuals with comorbidities, those case fatality would have been a lot higher. Only problem with case fatality is the longer the time between diagnosis and death, the more likely there will be some confounding variables or competing factors that may kind of occlude the conception that it was that specific disease that caused the death, right? So there are other factors may mix with the supposed cause of death. Talk about 5-year survival. This is used in cancer because most people with cancer die within 5 years. So it's the probability of surviving 5 years after diagnosis and treatment begins. Unfortunately, it is highly flawed. And one of the reasons it's flawed is because of screening and what we call a lead time bias. So there is it's kind of biased towards people who get screened in a sense. They seem to live longer. Actually, just some colleagues and I are submitting a paper to a cancer epidemiology journal where we looked at factors predicting colon cancer screening choice, whether it's going to be something more invasive like a colonoscopy or less invasive, say like Cologuard. But I had to mention lead time bias there because lead time bias is actually quite important. So let's take a look at this. This is a natural history of the disease. This time we're starting with susceptibility, not just infection, right? Susceptibility and then resolution, which in this case we're looking at death. So resolution is death. So two individuals, say one of them was diagnosed with cancer after clinical symptoms started. So here, clinical symptoms started over here, right? 5.2 years. So this person was diagnosed, right? Cancer was detected right after the symptoms occurred. And that person lived 3.6 years, right? So according to this, the person did not survive 5 years. But we have a success, right? We have a success for the person who was screened early. This individual got screening a much earlier period, right? And that individual apparently lived longer, 5.2 years, right? So there was an advantage clearly for getting screened. But here's the problem. The time from infection to death was 5.5 years for both individuals. It just appears that the individual who was screened lived longer. So this is what's known as lead time bias, and that affects this 5-year survival. So that's problematic as well as a measure of mortality. Other measures of mortality do exist, and they have something to do with what we call a survival analysis. Good stuff here. A good application of, I believe it's the exponential distribution. It's derived from the gamma distribution that shows you the probability of an event occurring after some period of time. This isn't a stats class. I do have a proof though, one of my videos about the gamma distribution if you're interested in that. But anyway, let's look at these life tables. We track survival from initiation of treatment or upon diagnosis. But this is an example from Gordis's the Gordis textbook, pages 120, the ebook 128 to 30. So just so we know where I am here, that should be in chapter 6. Yeah, 128 to 130. So they're right here. So observe survival. But this is an interesting example because it's not quite a realistic type example, but it's a good way to learn how to calculate survival using one of these life tables. This is also assuming that there was no loss to follow-up, which is a very, I wouldn't say absurd assumption, but it's a very unrealistic assumption. People do get lost to follow-up. But let's take a look at this. So we have people tracked for 5 years. At each year, we have new cases coming in, right? Being treated for a disease, right? So they're being treated. So the first year, 84 people came in, and those 84 people were followed for 5 years. Each year, there were some survivors. So almost 50% of the people died at first year, right? 84, we dropped down to 44 survivors, then 21 and 13, 10, and there were 8 people who survived 5 years. The second year, we had 62 people come in, and they were followed 4 years because we only had, let's just suppose this was a government-funded study, and we were able to track people for 5 years, right? Got an additional year, like say an R01 grant, you should get 5 years. You do the research for 4 years, but this case, we were able to extend it 5th year. We got like some extra funds or something, or an extension, right? So we follow them for 4 years, so we don't have the 5th year available. And in the 3rd year, another 93 people enter the study, and so on each year. So the last year, in this case, was 2004. We had 76 people entering. Those folks were only able to be followed for 1 year, right? Because then the study funding dried up. So we had a total of 375 people receiving treatment. So we could calculate what's the probability of surviving 1 year, 2 years, 3 years, 4 years, and 5 years. It's interesting that these probabilities are conditional, right? They're conditional. So like we'll calculate the probability of surviving 1 year. So everybody in this study was tracked for at least 1 year. So there were 375 individuals initially. 197 of those 375 survived, leaving us with 0.52, excuse me, leaving us with 197 of those people survived 1 year. So when we divided 197 by 375, we got 53% were able to survive for 1 year. Okay. What's the probability of surviving 2 years given you survived the first year? Well, we can calculate that as well, right? So let's look at this half of the screen here. So this is what we're doing is we're using the multiplication rule of probability to do this calculation. Whenever you have an and situation, it means that we're using a multiplication rule in probability. So for instance, we have the probability of surviving the first year and the second year given you survive the first year. And it is also conditional, right? multiplication rule actually involves a conditional probability and a probability. So this is the probability of surviving the first year times the probability of surviving the second year, given you survive the first year. So given that they're not, assuming they're not independent of one another, you'd have this condition, right? Probability of surviving the first year times the probability of surviving the second year, given you survive the first year, times the probability of surviving the third year, given you survive the next year, right? So that's the way we would you do this kind of calculation. Now, this is for a different example coming up. We'll do it in a second. But here we have, what's the probability of surviving the first year given you survive, what's the probability of surviving the first year, right? So that's, we said that was 52.5%, right? Next question is, what's the probability of surviving the second year given you survived the first year? So at the end of the first year, we had 197 people left. Of those 197, well, 197 minus 43 of those folks were available 2 years, right? These 43 people were not available for the second year. So in our new denominator here would be 197 minus 43, right? We're eliminating these 43 folks that were only followed 1 year. So to calculate the probability of surviving 2 years given you survived first year, well, 71 people survived 2 years. So we'd be calculating 71 divided by 197 minus 143, we get 0.461. So the probability of surviving 2 years means you survive the first and the second year, right? That's a and means multiplication. And the second year, given you survive the first, is 0.461. We could do the same for the next year, right? So the probability of surviving 3 years given you survive 2 years is 0.655, and then we go to 0.696 for 4 years, given you survived 1, 2, 3 prior years, and then 0.80 surviving the 5th year, given you survive the other years. It's interesting that the probability increases here because, well, the probability of surviving that long, given you survived 4 years, it's going to be larger. These people are luckier, right? They made it that far. So their probability actually kind of increases here, right? But the probability of anyone surviving 1, 2, 3, 4, 5 years is going to be a lot smaller, right? So this is an interesting example of a conditional probability and a life table, right? So here I ask, how would you calculate the intersection of events? Well, use the multiplication rule. Intersection events is the probability of 2 events occurring, surviving the first and the second year, and so on. This is a survival curve, that figure that goes along with that. So that's the probability of surviving, all 5, 1 year, 2 years, 3 years, 4 years, all 5 years, right? So this is different. This is probability of surviving all 5 years. So the first and the second and the third and the fourth and the fifth. That's different than saying, what's the probability of surviving the 5th year given you survive the other years, right? So this probability is higher, right? In fact, this would be 8 divided by 16 minus 13, right? So not 8, oh, sorry. Yeah, no, I'm sorry, not that. No, what I meant was, I forgot, that's the wrong one here. So it's 8 divided by 16 minus 6, not minus 13. 16 minus 6, because these 6 individuals were followed for 4 years, but not the 5th year, right? Okay, so that's 8 divided by 10, which is 0.80. So if you were able to survive this long, the probability of surviving 1 more year is pretty high, but the probability of surviving all these years, it means you'd have to survive the first and the second. Well, you can actually do that. Look, let's do that. Probability of surviving all 5 years, right? All 5 years, it's going to be much smaller. So it's 0.525 times 0.461 times 0.655 times 696 times 0.8 equals, it's very, very small. So there's like a 9% chance that one survives 5 years, but there's an 80% chance one survives the 5th year if they survived all the other years. So you see the difference? So if you were to just ask anybody, what's the probability that somebody survives for 5 years with this disease? It's very low, but given that they survive that long, the chances are pretty good. So we'd like to be able to have more people survive at least 4 years than, their life is cake after that, right? So you can see that the survival curve indicates that there's a lower likelihood of surviving all of those years. Okay. So let's do an example here. 430 individuals receive treatment for disease D, my favorite disease. What's the probability one survives 3 years post-treatment? All right, so let's do that. So this is what I was showing you earlier. The probability of surviving 3 years post-treatment is the probability of surviving the first year and the second year given you survive the first year, and the third year given you survive the second year, right? So that, of course, is a joint probability, and we use multiplication rule here, right? Because we have these intersections of events, and that's what we calculate here, right? So the probability of surviving 1 year, well, we have 270 divided by 430. Probability of surviving 2 years given 2 years, right? Well, see how many people, given you survive the first year, how many people survive? So we have 93 people survive. We're going to, denominator will be 270 minus 70 because these 70 people were only followed 1 year, not 2 years, right? So we got 93 divided by 270 minus 70. And then for the last year, we have 39 divided by 93 minus 18, right? 93 minus 18. So we get a whopping 15%, right? So probability of surviving 3 years is only 15%, okay? So again, this is assuming there's no loss to follow, but in a sense, we're kind of playing out with the idea of loss to follow, which we'll add over here. So attrition means loss, right? Loss to follow up means you're lost for the remaining waves of this. So let's say there's like this year, there's 5 years of data. In this example, there's 5 years of data collection. If somebody drops out in the second year, then and never comes back, they're lost to follow up. These are follow-ups, right? For the first examination, the first study. So if they drop out, they're lost to follow up. If somebody misses the second year but comes back for a third, they're not lost to follow up. They're just missing at that one time point. So let's take a look at how we would include losses, attrition, in our calculation of a life table. Okay, so this is going to be a little different. So the first year we started with 300. So now we're tracking these folks. Okay, no new people are coming into the study. We're just tracking 375 folks. So we had 375 individuals at the start of treatment, right? Of these 375, we had 178 died. 0 withdrew during that first period. We were lucky, nobody withdrew. We kept everybody during that first period. The effective number exposed to the risk of dying, that's the 375. The proportion who died during the interval was 0.475, so that's 178 divided by 375. I don't believe I show you that here. So that's the proportion who died. So the proportion of people not dying was 1 so using the rule of complementary events, the probability of, so if dying is defined as success, and that's only for statisticals, we use the term success, then failing to die is failure. So 1 minus success equals failure. The probability of failure equals 1 minus the probability of success, just like the probability of success equals 1 minus the probability of failure. So 1 minus 0.475 is 0.525. So the cumulative proportion surviving from enrollment to the end of the interval, the cumulative survival is 0.525. So that'll be the same as this right here. Second year. All right, so we had 197 people alive at the start of treatment. Why? Well, we do 375 minus 178 gives us 197. 83 individuals died during this interval. But we also had 43 withdrawals. We don't know, we don't keep track of exactly when they withdrew, or we may, but they withdrew somewhere in that period. So we deal with that. We don't always have access to those data, right? So we deal with those withdrawals, giving them like half credit. We say that they left that halfway through the study. So when we calculate the probability, the effective number exposed to the risk of dying, we half this value here, half HALV, halve this item. So 197 minus 1/2 HALF of 43, right? That's 21.5. So 197 minus 21.5 is 175.5, right? So that's our denominator here. 83 died, so 83 divided by 175.5. That gives us 47.3%. So that's a proportion dying. The proportion not dying is 1 minus 0.473 or 0.5275. So the probability of not dying is 52.7%. What's the cumulative proportion surviving? So that means they must have survived the second year and the first year. So we can multiply 0.527 times 0.525 and we get 0.277. So there's a probability of surviving 2 years, right? All right, what's the probability of surviving 3 years? All right, so now we had 197 at the start of the second year. We lost 83 people to death. Now these people get full credit because they're gone, right? So 197 minus 83 minus 143, right? So that's how many people we start with. 197 minus 83 minus 43, we start the third year with 71 individuals. So that's 197 minus 83 minus 43. We know 19 folks died here. We lost 16. So our denominator, again, will be 71 minus 1/2 of 8, 16, 1/2 of 16, which is 8. So 71 minus 8 gives us 63. 19 people died, so 19 divided by 63 equals 0.302. So it's the proportion who died during the interval. The proportion who survived is the complement of the proportion who died. So 1 minus 0.302 is 0.698. To find the cumulative proportion surviving from enrollment to the end of that interval, it'll be 0.277 times 0.698, which is 0.193. Notice though how this column increases as this column decreases. Again, so probability of surviving the fourth year given one survived the third year is going to be higher than the probability of surviving 4 years. Because to survive 4, you have to survive the first and the second and the third and the fourth. But to survive the fourth year, given you survive the third year, we're only looking at that interval of time, right? So in the end, we find that probability of surviving all 4 years using this process that we use to calculate the cumulative proportion. That's 12.4%. Probability of surviving 5 years given you survive 4 is 0.846. So again, we get that. You're lucky to make it that long. Awesome. All right. So let's task here. We're going to complete this table similar to what we did before. So we with the last example we start. So we're looking at fill in the second and third years of the table. So we want to know what's the probability of surviving 3 years or whatever this disease is, probably disease D again. So we had 400 individuals alive at the start of treatment. Let me drink some water. 178 died. We had none lost to follow-up or withdrew or anything. So the effective number exposed to the risk of dying is 400. 178 divided by 400, 178 deaths out of 400 is 0.445 or 44.5%. 1 minus 0.445 is the proportion not dying in that interval, 0.555. So the cumulative proportion surviving that first year is same, 0.555. Second year, so let's go here, second year. So alive at the start of treatment is 222, right? So it's 400 minus 178. We put in 222, right? We had 85 died and 40 were withdrew, right? So we have 222 minus half of this minus 20 gives us 202, right? 202. That's what I have here. See, it's 222 minus 1/2 times 40. Proportion who died was 85 divided by 202, 0.421, 0.421. The proportion not dying is 1 minus 0.421, which gives us 1 minus 0.421 is 0.579, 0.579. Always write a 0 before the decimal place. And to find what's the cumulative proportion, either you can go 0.555 times 0.579. I just like doing this, right? Because it gets easier over time, right? Because you don't have to do have so many terms. So we have 0.555 times 0.579. We get 0. Here it is, right here, right? 0.321, 0.321. Take off. All right, at the third year, how many people do we have alive at the beginning of the third year? So we had 222 alive at the beginning of the last year, minus 85 who died, minus 40 more who just were lost to follow up. So that gives us 97. Is that great? So 97, yeah, 397. So that's 222 minus 40, right? 82 minus 85 is 97. Okay, we had 21 died, 24 withdrew. So the effective number exposed to the risk of dying would be 97 minus 1/2 times 24, right here, gives us 85. 85 folks. All right, 85 is our denominator. 21 died. 21 divided by 85 is 0.247. 0.247. The proportion not dying during the interval is 1 minus 0.247 or 0.753. 0.753. And then if I multiply, so either again, I can go 0.555 times 0.579 times 0.573, but this number already accounts for both of the prior values. I said he had put a 0 in there, so I get like, what is that word? I like to use anal. Is that the word? Yeah, anal retentive. That comes from Freudian psychology, if you're not familiar. You multiply these two together and we'll get the correct answer, and it is 0.242, 0.242. So there you go. You have a 24% chance of surviving all 3 years. And again, surviving a third year, given you survive the second year, 0.753. Okay. I hope I said that correctly before. So this is just this year, given you survive the prior year. This is the probability of surviving all 3 years, right? I think I misspoke. I misquoted myself, as somebody once famously said. How can you misquote yourself? Yeah, evidently you can. If you're an athlete, misquote yourself. All right, this Kaplan-Meier method. So in those last methods, we used what's called discrete time. We had a specific time point. I think it's actually called discrete time survival analysis. And this method, Kaplan-Meier method, we don't use discrete time. And again, this comes from the textbook. This is text figure 612, not as pretty as mine, on page 134. Let's see, page 134. I actually contacted Gordis years ago and asked him, hey, do you want me to use some of my notes? He said, nah. I have my own textbooks now, but not for this course. So this is his figure right here, right? And then this is the table. So I just, I doctored it up, doctored it up, made it look prettier, I think. All right. So whenever a person dies, that's the end of one of these periods. That's the terminal point for each interval, right? End of each interval here. So if we look at this, oh, we had one person die at 4 months or years? That's whatever it is, 4 months. I guess it's months. one at 10 months, one at 14 months, and 24 months. And then you had people who are lost at follow-up. And we have to account for those individuals being lost at follow-up as well. So let's go ahead and do this. Let's see how it's done. Again, this is from the book. Yep. So times to death. So somebody died at 4 months, 10 months, 14 months, at 24 months. We saw that here, right? 4, 10, 14, and 24 months. That's when people died. Initially, we had 6 people alive. We were following 6 people. One of those people died during this first interval. The probability of dying, or the proportion dying, was 1 divided by 6, or 0.167. Proportion not dying is 1 minus 0.167. So look here, I show you the columns. This is beautiful, isn't it? 0.833. A cumulative proportion who survived to that time, or cumulative survival, is 0.833. So this is the same as what we just did a moment ago, right? We had, well, let's see, let's look at this here. When another person died at 10 months, but in between we lost one person, right? So there was a loss to follow-up. So at 10 months, we have 6 minus 1 person who died. That's 5 minus 1 person who's lost. We had 4 people alive, right? At the start of that next interval. Of those 4, 1 people died. The probability of dying was 0.250. Probability of not dying was 0.750. Cumulative survival, again, is 0.75 times 0.833. So there's 62.5% chance of surviving those 2 intervals. The next person died at 14 months. So we had 4 minus 1 death gives us 3. So we do the same calculation again. And then finally we get to 0.667 times 0.625. We get 0.417. And then we had another person who lost a follow-up plus a death. So 3 minus 1 is 2 minus 1 person lost a follow-up gives us 1. Well, probably proportion died was 1, right? 1 divided by 1 is 1. People surviving is 0. So really this tells us there was a 0% chance of surviving all during this entire time. Okay, that's using the Kaplan-Meier method. Now, it's interesting. Survival is this type of survival analysis, if we can call it. It's used often not just for deaths. It's also used when we have other types of survival. Like, for instance, in substance use, people quit. Like, say, in this case, I'm looking at smoking, cigarette smoking. People quit cigarette smoking, but then they relapse. So relapse is akin to death, right, in this case, because survival means you remain abstinent. So either you can remain abstinent or you can relapse. So suppose you're testing a new smoking cessation program for 10 heavy smokers. You're interested in tracking abstinence using the Kaplan-Meier method. The data are presented in table 4. This is table 4. This is not from the book. In addition to the relapse points, there are 3 individuals lost to follow-up. Lost to follow-up occurred as follows. 1 participant moved out of town at 14 months. I don't know why it's highlighted, but it is. And 2 individuals could no longer be located for tracking at 22 months. Complete the empty cells of table 4, not table 1. Table 4. There you go. I like to always bold table. Think of it like writing publications, manuscripts for publication. All right. So we have 6 months, number abstinence. So 1 person relapsed at 6 months. So at the start of the time period, there were 10 individuals, 1 relapse. So we have here, as you see, 1 divided by 10 is 0.10. Portion who remained abstinent is 0.90, like 1 minus 0.10 is 0.90, and the cumulative proportion remaining abstinent is 0.90. Okay, you got that. So 1 divided by 0.1, and then that's the proportion who relapsed. Proportion who remained abstinent is 1 minus the proportion who relapsed. Success is abstinence. Well, in this case, success is relapse, and the failure would be abstinence. We're tracking relapses. Again, we use this success and failure in statistics based on what we're looking for, not necessarily anything qualitative. Okay. So now we go to the second one. Let's see. at 12 months, well, there was one who relapsed, so 10 minus 1 is 9. I don't think anybody was lost to follow-up. We had one participant moved at 14 months, not yet, right? So now we have 1 divided by 9, so the number we relapse, one of those 9 individuals, and we get 0.111. The amount that remained abstinent was 0.889, because you either relapse or you remain abstinent, right? So now to get the probability of the cumulative proportion, sorry, who remained abstinent at this time, cumulative survival, as we call it, is 0.889 times 0.9 or 0.8, 0.8. Ta-da. All right, next step. Sweet. Okay, so this is the period where we lost one individual. We lost a person at 14 months. So one person relapsed, so that 9 minus 1 is 8, minus the other person who left, that gives it a 7, right? 9 minus 2 is 7. So we had 7 people start this interval, and one person out of those 7 relapse. So 1 divided by 7 gives us 0.143, 0.143. 1 minus 0.143 is 0.857. So that's the proportion that remained abstinent at that time. So cumulative proportion that remained abstinent is 0.857 times 0.80. So we're at 0.857. Or you can do this times that. So that's what I show here. 0.9 times 0.889 times 0.857 equals 0.686, 0.686. There you go. Ta-da. All right, so let's do the next one. And next, or the last one. So what else does it say here? One participant and 2 individuals could no longer be located for tracking at 22 months. So now we lost 2 people. So that's 7 minus 1 who relapsed, minus 2 more. 7 minus 1 is 6, minus 2 is 4, right? So this 1 divided by 4, the proportion relapsed is 0.25. The proportion who remained abstinent is 1 minus 0.25 or 0.75. And the cumulative proportion who remained abstinent is 0.75 times 0.686, or you can do 0.9 times 0.889 times 0.857 times 0.750, blah, 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 whatever you want to do. What did I write here? I have 0.9 times 0.889, 0.85. Oh, I wrote 0.8 here. Jeez, what? I wrote something wrong here. So let me do this correctly here. Just make sure I got it correct. Okay, so sometimes I do stuff like that. Let's see, let's clear this bad boy out here. So you got point. Wait, what did I do? What did I do wrong here? So I put the wrong number of people. See, I put 7 minus 1, and I wrote death, by the way. So being relapsing must be death in my mind, right? 7 minus 1 is 6, minus 2 is 4, but I wrote 5. Now see, shame on me, right? That's my mistake. My mistake. All right, so what was I going to do here? I got 0.75 times 0.686, 0.686, and we get 0.5145. 0.5145. All right, that's better. So you could see here the proportion, if you can make it through this time period, your probability of making it all, this whole time point, it still remains pretty high. The reason it declined a bit is because you lost those 2 people. Had we not lost anybody, this would have been even higher. But the proportion of remaining abstinent across all of this whole time period was 51.45%. Wow, that was good stuff, my friends. I want to thank you for another wonderful episode of, sometimes I like to call things the Rodcast, right? For my stuff. If you ever seen any of my live broadcasts. But anyway, thank you. This was fun. Enjoy. I hope you're having a great week. All right. Thank you.